Okay, so this time, uh, this time I will explain uh, about the natural radioactivity. Okay, so natural means uh, it means that the nuclides can be found or the radioisotope can be found in nature. Okay. Uh, okay. So first, there are four long series of decay chain. Okay. Uh, First one is uranium series. Okay. So it start with uranium 238. Okay. So the half life of uranium 238 is 4.5 10 to the power of 9 years. Okay. And after long decay chain, finally the series is stopped at stable lead 206. So to visualize this series, okay, you can Google it. Okay, so you try Google uranium series. Yes, let's choose a good image. This one. This one is not good resolutions. This one. Uh, I don't know if you can see it. Okay, let's open it new tab. Okay, so uranium 238. Okay, so we start with the parent nuclide, which is the uranium 238. Okay, the half life is 4.9 10 to the power of 9 years. Okay, so it's very long half life. Okay, and especially for uranium 238. Okay, the half life of it is said to be equal to the age of our Earth. Okay, so since the formation of our Earth, okay, it is said that the the age of our Earth is is nearly equal to the half life of this uranium 238, okay, which is 4.5 10 to the power 9 years. Okay. And then okay, and then alpha decay, okay, becomes sodium. Okay, and then after that beta minus decay becoming protactinium, okay, and then uranium 234, and then thorium, radium, radon, okay, polonium, lead, bismuth, okay, uh, polonium, lead, okay, and then from bismuth, uh, thallium, okay, and thallium to lead to bismuth, bismuth to polonium, okay, and finally, okay, uh, if you uh, follow the trend, okay, you will you will reach the stable like 206. Okay, which is stable. Okay, astatine, I'm not sure why astatine here. Okay, why the astatine is included here. Okay. Let's check other. So there are many uh figures. Okay, there are many figures. So just now is an example. Okay, so okay. So this one, uh, ascertine is actually from polonium. Okay, polonium. So there's a missing arrow. Okay, in this diagram. Okay. This one is more complete. Okay. So 92. This is the atomic number is 92. This one is 90. Okay. It's 92. Okay. So the vertical direction, the vertical axis shows the uh, atomic number. Okay. If you go upwards, means the atomic number will increase. Okay. And if you go the horizontal direction is the number of neutron. Okay. So if you go to the right, okay, in this figure, if you go to the right, means that your uh, your neutron number will increase. Okay. Oh no, will decrease. Okay, will decrease. So this is a figure. Okay, if you look at other figure, the representation will different. So be careful with what you see. Okay, for example, this one. Okay, this one. Okay, this one the style is different. Okay, if you go to the right, okay, horizontal direction. Okay, uh, the atomic number is increasing. Okay. Okay, perhaps this is more comprehensive. Okay. So to the right, increasing in atomic number. Okay. To uh, to the upwards, the increasing number in neutron. Okay, but in this figure, the symbol, okay, the symbol is not what we are familiar with. Okay, like this one U1, this one UX. Okay, U1 supposed to be the thoric, is supposed to be the uranium 238. Okay, so be careful with what you are seeing. Okay, I think this one is more this one is complete. But the resolution is poor. Okay, so anyway, this is an example of a decay series. Okay, and for this series, okay, for this series begin with uranium 238. Okay, it's also called 4n plus 2 series. Okay, so why they call it 4n plus 2 series? Okay, because if any nuclides in the series, okay, its its main number is equal to 4n plus 2 equal to, let's say for example, let's say uranium 238. Okay, so 4n plus 2 equal to 238. Okay, so 4n equal to 238 minus 2. Okay, 236. Okay, and n equal to uh let me use my calculator. 236 divided with 4. Okay, so 49. Okay. So if you do the same thing, if you do the same calculation for all the nuclides, okay, you will get n, you will find that the n is a positive integer. there's no remainder. In the calculation, there will be no remainder. Okay, so in uranium series, okay, so it will follow 4n plus 2. So any nuclides, so the mass number of any nuclide in uranium series will follow 4n plus 2. Okay, with the n is positive integer. Okay, and okay, for thorium, okay, let's see the thorium series. Okay, thorium series. Okay, okay, this one. Okay, thorium 232. Okay, if you divide with 4, there will be no remainder. Okay, so 232 divided with 4, you get 58. Okay, and then let's say let's try bismuth. 212 divided with 4, it is 53. Okay, so any nuclides, if you try, it will exactly so the mass number of each nuclides will follow 4 time ends. Okay, and okay, and thorium. Okay, so thorium series, okay, start with thorium 232 and with lead 208. Okay, while the actinium series start with uranium 235, okay, and with lead 207. Okay, of course you don't have to memorize all this. This is just for your information, okay, for your knowledge. I don't ask. You don't have to remember all this. Okay, when you want the information, you can search it. Okay, and then okay, let's see the actinium series. Let's check the actinium series. Okay, actinium series. This is thorium. Actinium series should start with uranium 235. Okay, this one, uranium 235. Okay, so let's see polonium 215. Okay, polonium 215. Will it follow the 4n plus 3? 215 polonium. Okay, equal to 3 plus 4n. 4n equal to 212. So n is 53. Okay, so that is the actinium series, which is called 4n plus 3 series. Okay, so all this so all the paranuclides, okay, so all these 3 paranuclides, uranium 238, thorium 234, or uranium 235, currently, okay, at the present time, are found in nature. Okay, they can be found in nature, but for neptunium series, okay, you can in nature you can no longer find neptunium 237. So the neptunium 237 half life is 2.1 10 to the power of 6 years. Okay, so okay, for neptunium series, it ends at stable 209 bismuth. Okay, so why neptunium there is no more neptunium series at the present time? Okay, so, let's think. Okay, now let's think about the half life of all these paranuclides. Okay, let's say this is the timeline. Okay, and this is when, okay, let's say this is the birth of the earth. Okay, this is the let's This is what they claim the the birth of the Earth. Okay, and this is the present time, okay, which is 4.9 10 to the power of 9 years. Okay, so if you, it's right, if you find it is hard to believe this is the age of our Earth, try to do some search. So it will be so the age of our Earth is around 4.510 to the power of 9 years. Okay? So at the birth of the Earth, okay, then we had uranium 238. Okay, by the way, you can express nuclides. Okay, let's say uranium 238. Okay, by writing uranium 238 or 238 uranium or uranium 238. Okay, like this. So all the notation imply the same thing. Okay? So sometimes I wrote this way, I write this way. Sometimes I write this way. Sometimes the book write this way. All mean the same thing. Okay. So uranium 238, okay, and then thorium 232, and then uranium 235, then the neptunium 237. Okay. So if you compare to the present, if you consider the beginning of time to the present time, okay, the uranium 238, okay, the half life of the uranium 238 is exactly what we are now, okay, what we are at the present time. So meaning that uranium 238, the uranium 238 or uh, mean, so all the uranium 238 nuclei on this Earth, okay, have decay, okay, have decay uh, for only one half life, okay? One half life, meaning that uh, there is there are still, okay, there is still 50% of uranium 238 present at the current time. So here is, let's say here is, let's say the beginning of time is 100%. It should be 100%. Okay, now after one half life, so we should expect the number of uranium 238 has been decreased to 50% from its original number. Okay, and thorium, thorium 232 is half life is much longer than the age of our Earth. Okay, meaning that at the present time they are not, the thorium nuclei, okay, are not yet undergo one half life. Okay, so we can expect the one half life of thorium 232 is far away from the current time. Okay, so which means that thorium 232, okay, is still a lot. There are many thorium 232 currently on our planet. Okay. However, the uranium 235, okay, the uranium 235 is the half life is a bit shorter, okay, a bit shorter than the age of our Earth. Okay, so we can say that it's undergo its first half-life is somewhere before the age of our Earth. Okay, let's say it could be, this is not according to the scale. Okay, so don't get it wrong. So it could be around here. So so what I'm trying to say here, it is before the present time. Okay, so this is the one half-life of the uranium 232. Okay, and com- and compared to these three, okay, this 1, 2, and 3 parent nuclei, okay, neptunium is far shorter half-life. Okay? So on the timeline, okay, it is long. It has been undergo its first half-life long time ago, and at the present time, okay, uh, the neptunium, okay, has undergo many time of uh, half-life, okay, which make it existence almost zero, okay, almost 0%, okay, which is the reason why you cannot find neptunium in the nature anymore. Okay, so okay, so let's try to calculate quantitatively. Okay? And we know that the present number of nuclei, okay, is equal to its initial number, okay, multiply with the exponential minus lambda t. So now think about uranium 238. 238 uranium. Okay, so the ratio of the present number of uranium 238 to the initial number of uranium 238, okay, is the exponential minus lambda t. Okay, so exponential minus lambda, okay, minus lambda, we know ln 2 over the decay constant. Okay, the decay constant of uranium 238 is 4.5 10 to the power of 9 years. Okay, 4.5 times t is the present time, okay, which is 4.5 to the power of 9 years. Okay, so what you will get here is, if you try calculate this, you will get exactly 0.5. Okay, so meaning that at the present time, so compared to the initial time, okay, at the current time in 2021, okay, uh, there are 50% of uranium 238 remains. Okay, which is why you still can find, you can easily find uranium 238. Okay, now if you do the same for uranium 235, okay, uh, and t over n not n0 equal to e exponential minus ln 2 over uranium 235, 7 and power of 8. Okay, 7 10 to the power of 8. Okay, and the present time is 4.5 9. Okay, So you will get about 0.012, okay, which is in fraction, okay, it will be 1 over 86. Okay, so at the present time only, okay, only 1 per 86 uranium 235 remains, okay, which is what, which explain why if you if you go to the uranium mining field, okay, if you go to the uranium mining field, okay, let's say you take out the uranium ore, okay, and you will find that within the ore 99.3% is uranium 238, okay, and the rest, which is 0.7%, is uranium 235, okay. And in nuclear in nuclear reactor, okay, you need uh a little more concentration than 0.7, so that you can operate your nuclear reactor, and that will be explained in another video, okay, in the future, okay. So now, this calculation is the proof of why the natural uranium in the natural uranium ore, 99.3% is represented by the uranium 238, and the rest, which is 0.7%, is only by the uranium 235. Okay, and if you do the same thing for, okay, we don't have to do the thorium 232, because still it is still not yet reaching its first half life at the present time. Okay, so there are abundance of there are a lot of thorium 232, which is why at the present time, okay, there are a lot of research on thorium 232 as a nuclear fuel. Okay. Because we have a lot around the globe, okay, but not in Malaysia, unfortunately. So okay, so neptunium, okay, let's try neptunium. So if you do neptunium, okay, you will get far smaller number than what is calculated here, because the half life of neptunium is in the order of 10 to the power of 6, okay, compared to the uranium 235 in the order of 10 to the power of 8. So we should expect that this ratio is far smaller, okay, far smaller the uranium 2 than for the uranium 235. So which is why at the present time you cannot find neptunium 237, okay. But artificially it is produced in nuclear reactor. Yeah, that's a different story. So other than this long decay series of radionuclides, okay, in nature you can find you can find radionuclides, which not in long series but available in nature, which such as potassium 40, hydrogen 3, which is tritium, beryllium 7, barium 10, carbon 14, as well as uh, sodium 22, so on and so on. You can, if you want, you can investigate it by your own self if you want to know more. Okay, so so if you are asking, just now I explained only the parent. Okay, the explanation was were on the parent. Okay, if you might ask, if you ask yourself, you might ask yourself, what happened? What about their daughter nuclides? Okay, so that's are they still present at the are they still exist at the present time? Okay, the answer to that question uh, from from the uh, it's not easily cannot be easily determined from the decay chain. Okay, uh, okay. So it depend on the amount. Okay, it depend on the amount of the daughter the daughter nuclides as well as their half life. Okay, so I think that's all for a natural radioactivity. Thank you.